All right, good morning, everyone. Welcome back to our second day on this beautiful, gloomy Tuesday morning. Life looks fantastic. So let's kind of pick up where we finished off last time. So kind of a quick recap of what we talked about. So again, we started with simple harmonic motion. And again, simple harmonic motion is anything that repeats itself pretty much indefinitely after it has started moving. The reason for that, again, is that because it's a restoring force and that the acceleration is dependent on the position. So in that case, by the time it returns back to its initial position, it has zero acceleration, so it has too much inertia, so it keeps carrying past where it was and then undergoes simple harmonic motion. So again, we wrote down some general things. So first off, we had general. So if I was dealing with, say, a spring mass system, here we then have, clicking on wrong buttons, there we go. So we have the position as a function of time is equal to the amplitude times cosine of the angular frequency times the time plus phi, which is what, again, we call the phase factor. Now, if I was dealing with something like a pendulum, which is what we're going to be dealing with today, we would just replace x here with typically theta, which would be the angular position. But again, we'll talk about that as we go through. We also know that the acceleration is equal to minus the angular frequency squared times the position, so that the maximum acceleration is then equal to angular frequency squared times the amplitude. The maximum velocity is then equal to the angular frequency times the amplitude. We also know that the total energy is equal to the kinetic energy plus the potential energy. So in this case, this is going to be equal to 1/2 of the mass times the velocity squared plus then the potential energy. Okay, so I'm going to leave it simply as potential energy, even though yesterday we looked at specifically a spring mass system, but we don't have to have a spring mass system. This could be, again, a simple pendulum, which has a different type of potential energy. And then we also talked about that the total energy then, if it initially starts off at the equilibrium position, is simply going to be equal to the maximum kinetic energy. So again, these are all of the things that are constant all the time. And we also know that 2 pi times the frequency, oops, I told you I was going to use a different frequency. There we go, 2 pi times the frequency, there we go, is equal to the angular frequency, which means that the period is equal to 2 pi divided by the angular frequency, because remember that this is the same thing as 2 pi divided by the period, since the period is inversely related to the frequency. So these are all the general quantities that we talked about. So again, this is true for any type of harmonic oscillator. What's going to be different for each type of harmonic oscillator is that angular frequency. So far we've seen specific. The only specific we've seen is for a spring mass system. That's the only type that we've talked about so far today. So here we have our spring attached to some sort of mass. So this has a spring constant K and a mass of M. So here we said the angular frequency then is equal to the square root of the spring constant divided by the mass. So one thing I wanted to point out before we move on is this quantity here, then the period. So if I was looking in the specific case of a spring mass system, what that means then is that our period is going to be the same thing then as 2 pi times the square root of the mass divided by the spring constant, which basically means that it's independent of the amplitude. So this quantity here is independent of amplitude, which means that it doesn't matter how far I move my spring mass system here. All that matters is that it has a particular mass attached to a particular spring. So for example, if I, again, bring up our favorite simulation here, what that means is it doesn't matter how far I pull the mass here. So here I have 100 grams attached to a spring, which has a particular spring constant. Same 100 grams attached to the same spring. So in this case, it doesn't matter if I pull it down, oops, say this far, and let it oscillate. Let me put this in slow motion. Or if I pull it down only a fraction of that distance and let it oscillate, let me get back to its amplitude here, and then let it oscillate, the period of oscillation for each one of these systems is identically the same. So as long as let me do that again. So if I put this on here, this guy on here, stop each one. So if I pull this guy down this far, let it go, again, put it in slow motion, pull this guy down, say a fraction of that distance, and now let it go. The period for each one of these guys is identically the same. So if I pull out my stopwatch here, let them both go to the amplitudes, run our stopwatch, and we can see that they both reach exactly the same amplitude part, and in this case, 0.81 seconds. So the interesting thing is that the amplitude, or at least the period, is completely independent of the amplitude. It doesn't matter what the amplitude is, the period is exactly the same. So the period for at least the spring mass system is dictated only by the amount of mass that I put on the spring and that spring constant. It doesn't depend on anything else, which is kind of interesting. So it doesn't depend at all on this amplitude. So I just wanted to point that out before we actually move further. So now that we know all these things, so first thing we're going to do is let's do a couple examples and see how this stuff works. So the first example we're going to look at is this one. So this says that we have some mass here. This has 0.65 kilograms initially at rest attached to a spring, where that spring has a spring constant of 184 newtons per meter. And then at time is equal to 0, I'm going to take this hammer here and hit it and give this thing an initial velocity of 2.26 meters per second. So in this case, let's say I hit this thing, so it's at its equilibrium position. This thing is now going to move to the right with an initial velocity of 2.26 meters per second. And we want to know is these particular quantities. So we want to know what's the period and the frequency. What is the amplitude? So how far is this thing going to move away from its, pardon me, away from equilibrium position? So it's the maximum distance, maximum displacement. The maximum acceleration, which we can get from that amplitude. The position as a function of time. So in this case, we need to know what is that phase factor. And then the total energy, and then how much kinetic energy is this thing going to have when it is 0.4 times the amplitude away from its equilibrium position. So, so let's recap everything that we know. So here we have our spring. Here's our mass. So our mass was what, 0.65 kilograms, if I remember correctly. This was 184 newtons per meter. And we're going to give it an initial velocity in this direction, v0, which is 2.26 meters per second. So the first thing we want to know, A, is what is the period equal to, and what is the frequency equal to? So we want to know what is that guy equal to. So the nice thing about this part of the question then is what? Once we know the period, we know the frequency, or once we know the frequency, we know the period. So either way that we know, whichever one comes first. So good. So how would I do this part? So how would I do this part of the problem? So which one should I try to find first? The frequency or the period? Again, doesn't really matter, but let's think about what it is that we know. So how would I do this problem? How would I do this part?
I would probably try to find the period first.
Good, sounds good. So let's look at the period. So we know the period then is equal to, so let's go back to where we wrote down on the previous page. So according to this, the period is 2 pi divided by the frequency, or we wrote over here, that's 2 pi times the square root of the mass divided by the spring constant. Do we know the mass in this case? Yes. Do we know the spring constant? Yes. So good, we know everything. So let's plug that in. So we know that the period then is equal to 2 pi times the square root of the mass divided by the spring constant. So it's going to be the same thing as 2 pi times the square root of 0.65 divided by 184. So plug in our numbers. We find in this case then is that the period should be about 0.37 seconds. 0.37 seconds. Okay. Now that we know the period, again, we know the frequency is simply 1 over the period. So in that case, we just invert this, which works out to be about 2.7 hertz. Okay. So good. So good. Now part B, what we're looking for part B. So part B, we're looking for the amplitude of oscillation. So we want to know what is the amplitude. So how would I do that part of the problem? So how would I find the amplitude? So any ideas? How would we find the amplitude in this case? Everybody's so quiet. So what do you think? How would we determine the amplitude from what it is that we know?
I would use the period to find the angular frequency first.
Okay.
Maybe, and then use that to find the amplitude.
Okay, and how would we find the amplitude? So good, you're absolutely right. So we could say, well, in this case, we know directly, we can say the angular frequency is just the square root of k over m. So we have that much information. So we actually don't have to use the period, but we could if we didn't know m and k. So that's good. So how would I then, which formula would you want to use then to determine E? So now that you have this guy, so let's go back to our previous page. So which one of these formulas that we wrote down would give you the amplitude? So continue your thought. So what do you think?
The velocity max.
Good, very good, that's right. So here we would use the velocity maximum. So going back to our problem, do we know the maximum amount of velocity? Well, yes, we do. That is just the V0. The initial velocity is the maximum velocity because we know initially our system is at equilibrium. We know there's no acceleration. We know it has the maximum amount of velocity there. So here we know that V max is actually equal to the initial, which is equal to the angular frequency times the amplitude. Right. So in this case, our amplitude then is going to be the initial velocity divided by the angular frequency. So in this case, that's going to be the same thing as what? So that's going to be the square root of k, m over k times the initial velocity. Good. So plug in our values, that works out to be about 0.13 meters is then our amplitude. Good. So this thing is going to make an amplitude of 0.13 meters. Good. Very good. So part C. So part B says that we're now looking for the maximum acceleration. So A max. So again, going back to our equations that we wrote down, we know that A max is simply the angular frequency squared times the amplitude. So in this case, we know this is equal to omega squared times A. So omega, again, we know is the square root of k over m. So this is going to be k over m times the amplitude. So that's going to be 184 divided by 0.65, all times 0.13. So plug in our numbers. This works out to be about 36.8 meters per second squared. So this is our maximum acceleration. Good. Now part D, we now want to write this as a function of time, which basically means that for part D, we want to say x of t is equal to a times cosine of omega t plus the phase factor. So to write this, we know the amplitude. We just solved that. We know the angular frequency. So what we're looking for in this case then is what's the phase factor. So there's two ways we can do this. Either we can solve for the phase factor directly, which we don't quite know how to do yet. We'll do that in the next example problem. Or we can think about the motion of this harmonic oscillator, which basically means that if I thought about plotting the harmonic oscillator versus time, so initially, if we go back to our problem, so let's go back to here. We know initially our harmonic oscillator, or at least our mass is at the equilibrium position, starts off on the initial velocity, which means it's at x is equal to 0, goes out to the amplitude, turns around, go back to x is equal to 0, goes to negative amplitude, back to x is equal to 0. So if I plotted this thing, it would look like this. So this thing would go out to the amplitude, down to minus the amplitude, back to the amplitude, and etc. So is this a cosine curve or is this a sine curve?
Cosine? No. Oh. I've forgotten which one starts with the word.
That's okay. This is actually a sine curve. So sine starts off at 0. Cosine starts off at maximum. That's right. So this is a cosine curve. There we go. So this one's cosine, and this one is sine. Good. So this is actually a sine curve. So in this case, we wouldn't actually have to determine the phase factor. We could just simply write down, well, since this thing is a sine curve, we can actually write this as a times sine of omega t. So that's it. So here, this thing as a function of time, we just write as 0.13 meters. That's our amplitude, times then sine of the square root of k over m, which is 16. Oops. There we go. 16. Oh, that's horrible. Okay, let me see if I can erase that. There we go. Okay, where am I? Here we go. 16.82 radians per second times time. So that would be our description of the position as a function of time of our oscillator. Part E, we're not looking for the total energy, so let's talk about part E. So the total energy is going to be equal to either, again, the maximum kinetic energy or equal to the maximum potential energy. So either one of these are appropriate. So if I'm looking at the maximum kinetic energy, I can write it as 1/2 m times v max squared. Or I can write it as 1/2 k times the amplitude squared. So in our case, we know both of these, right? We know the mass, that's given. We know the maximum velocity, that's also given. That's just the initial velocity. So in that case, we could just use the first one. So that would be all quantities that we know. So we wouldn't have to use anything we calculated. And the second one, we're given the spring constant. We've just calculated the amplitude, so we could use that one as well. But in a lot of cases, it's better to use the first one, to use numbers that are actually given to us instead of numbers which are calculated. So if we wanted to determine the total energy, it would actually be easier to use the first one because it would just be 1/2 mass times the initial velocity squared, all given quantities. So that'd be 0.65 kilograms times, there we go, times the 2.26 meters per second, 2.26 meters per second, quantity squared. So square all that out, we find then is that the total energy is 1.7 joules. Okay. So that's our total energy. So finally, the last part of the question says, for part F, we want to know what is the velocity equal to, or at least, sorry, what is the kinetic energy equal to? So what is the kinetic energy equal to when the particle is at 0.4 times the amplitude? So this is what we want to know. So when the mass is at 0.4 its amplitude, we want to know how much kinetic energy does this thing actually have? Well, we know from conservation of energy that, again, the total energy must be equal to the kinetic energy plus the potential energy at any point. So here, this is simply going to be equal to the kinetic energy, which it is that we're looking for, plus then 1/2 the spring constant times the position at which it is at squared. So in this case, this is going to be equal to the kinetic energy plus 1/2 the spring constant times 0.4 times the amplitude squared. So the kinetic energy in this case then is simply going to be the difference between the total energy and the potential energy. So from here, we can say the kinetic energy then is going to be the same thing as the total energy minus then the potential energy, which is the 1/2 spring constant times 0.4 amplitude squared. So this is how much kinetic energy it has. Plug in our numbers, find in this case that this is 1.45 joules. So this is how much energy it actually has, how much kinetic energy it has, so how fast it's actually moving. So, any questions on any part of these? Everybody doing okay?
For part D.
D, yes.
Where did you get the 16.2 radians per second?
Oh, so that just came from taking the, oops. So from part D, that just came from saying that omega was equal to the square root of k over m. So that's the same thing as the square root of the 184 divided by 0.65, which works out to be 16.82.
Okay.
Okay. And since this thing has units of radians per second, same thing as the angular velocity that you saw before. So, yeah.
Okay.
Sorry about that. Skip many steps. Can't help it. Okay. Everyone doing okay? Not too bad, right? So let's do another one. So the next one we want to look at is, so we're done with that one. Let's get rid of you. Good. So next one we want to look at is dealing with the phase factor. So how do we actually determine the phase factor? So this says that we're told that our simple harmonic oscillator is described by our usual equation. So position as function of time is equal to the amplitude times cosine of omega t plus the phase factor. And then we're told where the particle is, or where the mass is, at time is equal to 0 for all these different cases. So for case A, it's at negative of the amplitude. At case B, it's at the origin, so it's at equilibrium. Case C, it's at the amplitude. Case D, it's at half the amplitude. Case E, it's at negative half of the amplitude. And then finally, case F, it's at the amplitude divided by square root of 2. So we want to determine then, from these initial positions, what is this phase factor? So how will we determine this phase factor? So first off, again, we know that x as a function of time is equal to the amplitude times cosine of omega t plus the phase factor. But we're looking at x when t is equal to 0. So x of 0 then is equal to the amplitude times cosine of omega times 0 plus the phase factor, which is the same thing then as a times cosine of the phase factor. Okay. So basically what this says then is what? If we want to determine the phase factor, all we then have to do is what? Divide both sides by the amplitude and then take an inverse cosine to isolate then the phase factor. So from here, if we take the position at time is equal to 0 divided by the amplitude and an inverse cosine of that, that's then the same thing as the phase factor. So for each one of these different scenarios, to determine the phase factor, all we would have to do then is know the initial position, its amplitude, take an inverse cosine of that, and then I would determine the phase factor. So here, start off with part A. So for part A, what we know is that the position at time is equal to 0 is equal to negative of the amplitude. So using this says that our phase factor then would be equal to the inverse cosine of negative the amplitude divided by the amplitude, which is the same thing as cosine of, or the inverse cosine of 1. So, or sorry, negative 1. There we go. Negative 1. So when is cosine equal to negative 1? So for what angle is cosine equal to negative 1? You know, pull out some trig that you guys probably haven't thought about in maybe 100 years. So when is cosine, so for what angle is cosine equal to negative 1?
180.
What was that? That was a whisper.
180.
180. Good job, Taylor. That's right. So 180 degrees. So, but here we're not really dealing with degrees. We're going to deal with radians. So what's 180 degrees in terms of radians?
Pi.
Pi. Good. So here, our phase factor then is simply pi. Good. Exactly. So that means if we plug that back into our position as a function of time, which it doesn't ask us to do, but let's just do it anyways. So that means x of t then would be equal to a times cosine of omega t plus pi. But anytime I shift anything by pi, that's the same thing as negative a times cosine of omega t. Now, again, it doesn't ask us to do that, but let's just write it down anyways, just for fun. Let's look at b. So b now tells us that x0 is equal to 0, which means that our phase factor then is going to be the inverse cosine of 0 divided by a, which is the same thing then as inverse cosine of simply 0. So when is cosine equal to 0? So for what angles is cosine equal to 0?
90 and 270.
90 and 270, good. So that's the same thing as pi over 2 or 3 pi over 2. Good. Now what's interesting about this case is there's actually two angles which satisfy this, as opposed to this case, which was there was only one. And if I think about from 0 to 2 pi, here cosine is only -1 when it's at pi, but here cosine is equal to 0 for both pi over 2 and 3 pi over 2. So there's actually two answers in this case, where in this case there's only one. And I'll point that out more in just a second. So part C, we're talking about that x of 0 is equal to the amplitude. So here we get the inverse cosine of 1, right? So our phase factor in this case is simply inverse cosine of 1. And when is cosine equal to 1? So for what angle is cosine equal to 1?
0.
0, good. So here, this is simply 0. So again, in this case, there are only one answer. For this case, in this case, there are two answers. So.
First part C, could we say 2 pi?
For which one? For part C?
Yeah.
You could, yeah. So you could do 0 and 2 pi. Yeah.
But not if that complicates things.
Well, I mean, it's technically correct. I mean, actually, this would also be true for 4 pi, 6 pi, 8 pi. So this is actually true for any even multiple times pi. But if we just want to think between 0 and 2 pi and not actually include 2 pi, then you would just say 0. But you're absolutely correct. So if I thought about this as something which is repeating itself, then it would be 0 and 2 pi and 4 pi and 6 pi and 8 pi and etc. So any even integer multiple of pi. But if you don't want to confuse yourself, just say 0. That's fine. All right, good. So let's look at part D. So part D then says, now we have x of 0 is equal to a divided by 2. Right? So in this case, we then say our phase factor is the inverse cosine of 1/2. Okay? So 1/2 is a little bit trickier. That turns out to be pi over 3. So I'm going to ask you guys that one, but that's simply pi over 3, which is actually the same thing as negative pi over 3, which is the same thing as what? So what is that? So that's 5 pi over 3, I believe. So the same thing as pi over 3 and 5 pi over 3. So this one again has two answers. Part E, we then have, which is part E, negative a over 2. So we have x of 0 then is equal to negative a over 2. So here we have our phase factor then is going to be the inverse cosine of -1/2. So -1/2, that's going to be equal to plus or minus, oops, go away, there we go. Got all excited, there you go. plus or minus 2 pi over 3. And then finally, part F, we then have x of 0 was equal to a divided by the square root of 2, which means our phase factor then is going to be the inverse cosine of 1 over the square root of 2. Anybody know where cosine is equal to 1 over the square root of 2 or square root of 2 over 2? So for what angle is that true? It's okay if you don't. That would be 45 degrees. So that's actually going to be plus or minus pi over 4. It's plus or minus because remember that if I thought about my quadrants, cosine is positive in both the first and the fourth quadrants, which means you're looking at this angle here of pi over 4, or this angle here of negative pi over 4. Right? So what's the point of all this? So first of all, the point of all this is to, again, first see how we actually calculate the phase factor. And again, the phase factor is determined solely by where is this thing at time is equal to 0. But it's a little more complicated than that because, as we see, only in cases A and C, there's actually one answer. And the reason for that is because here it's at the amplitude, or negative the amplitude. For part C, it's at the amplitude, which means that in both of these cases, they have 0 velocity. Because when it's at the amplitude, it has maximum acceleration, but 0 velocity, which means we technically know both the velocity and the position. But for parts B and all the remaining, so D, E, and F, we only know the initial position, but we don't know the velocity. So here, we couldn't say if this thing was, the phase factor was either pi over 3 or negative pi over 3. We couldn't tell that until we knew the actual initial velocity as well. So in most cases, to know the phase factor exactly, you have to know not only the initial position, but the initial velocity as well. So we have to know both of those things to fully specify what the phase factor is. So ultimately, the point of all this is that to fully know the phase factor, we need to know both its initial position at time is equal to 0 and its initial velocity at time is equal to 0. We have to know both of these things. Otherwise, we don't know the phase factor fully. Now, for most problems that you're going to work on, whether it's going to be homework or on the exam, typically I'm going to either give you the phase factor or I'm going to give you information to let you know what the phase factor should be. So again, like the problem that we did earlier, what I said is that the hammer hit it when it was at its equilibrium position. So in that case, you know it's a sine curve. Or I'm going to tell you it's displaced by its maximum distance and then let go. In that case, you know it's a cosine curve, so you know what the phase factor is for both of those cases. But again, in a general scenario, you won't know exactly what the phase factor is unless you know both of these two pieces of information. And one other thing I want to talk about before we move on to the next part is we know the position as a function of time, but what are the velocity as a function of time? And what's the acceleration as a function of time? So these are two other quantities that we want to know. Well, in a calculus setting, to find the velocity, we would take the first derivative of the position to then get the velocity. To get the acceleration, we would then take the first derivative of the velocity or the second derivative of the position. Well, I'm just going to write those down here. So here, the velocity as a function of time then is going to be negative the amplitude times the angular velocity times sine of omega t plus phi. And then the acceleration is going to be negative the amplitude times the angular frequency squared times cosine of omega t plus phi. Okay. So these are the last pieces of information that we need. So good. So now we want to start looking at more types of simple harmonic oscillators.
Can you go back to that? Can you go back to that page for like just a second?
Sure. To here?
Yes.
You have questions about them, or you just didn't copy everything down yet?
I just was still writing down the second one, but
Sorry. Yeah. No, bro. So good. So good. So now we want to start looking at other types of harmonic oscillators. So another good type of harmonic oscillators is, as we talked about yesterday, my keys. Pendulums. So here, if I took my keys and I displace it to the side and I let it oscillate, this is a particular type of harmonic oscillator. It's obviously not a spring mass system, which means that that angular frequency, the square root of k over m, will not work in this case anymore, because first of all, there is no k. This thing is not a spring. It does have an m to it, right? There is a mass down here, but that omega is not going to work anymore. So what we want to do is do kind of what we talked about yesterday, using the sum of the forces to then extract exactly what this angular frequency is. So this is one type of pendulum we can have. Another type of pendulum I could have would be this, where in this case I can hold my water bottle up here, displace it, and again this thing is going to harmonically oscillate back and forth. The difference between these are they're both pendulums, but this one is what's known as a simple pendulum, where this one is what's known as a physical pendulum. So a simple pendulum is something which is made out of a string, typically going to be a massless string, attached to something at the end which has a mass to it, usually called a plumb bob. Where this one, which is what we call a physical pendulum, is something which is called a rigid body. So hopefully you remember these from 175. A rigid body is an object which does not deform under rotations. So it keeps exactly its form. So typically you're dealing with discs or rulers or rods or etc. So what we want to start doing then is start looking at these pendulums. And we want to extract what are the angular frequencies for these different pendulums. So here's our pendulums. So our first one, again, is what's called a simple pendulum. And then our other one is what's known as a physical pendulum. So we're going to look at both of these two different cases. So a simple pendulum is just a massless string attached to a mass. So in this case, I would just have a string with a mass m attached to it, and we're going to displace it away from its vertical equilibrium position. So this is our equilibrium position. And as I mentioned at the beginning, so here, instead of writing this in terms of x, we're going to write it in terms of theta. Physical pendulum then is going to be a rigid body, which again does not deform under rotation. So this is what we call a physical pendulum. So in this case, this would be some sort of, let's say, here's my object. Here's going to be my pivot point. So this is our pivot point. And again, this thing's going to be displaced away from the vertical position. Okay. There we go. Here is my vertical by some sort of angle delta theta. Okay. So we want to know in both of these cases then, what is omega? What is this angular frequency for each one of these two different scenarios? Now again, going back to what we talked about at the very beginning, the nice thing about this is all of these expressions that we wrote down here are all valid for this type of pendulum or this type of harmonic oscillator as well. The only thing that's going to be different, again, is now instead of calling this x, we're going to call it theta. But what's going to be different, again, is these omegas. The omega is the only thing which is going to be different. So instead of having this omega equal to the square root of k over m, it's going to be something different. And we want to know, what is that something different? And again, the way we're going to determine what omega is by using the fact that, again, our acceleration has to be equal to omega squared times the position. So this is something we talked about yesterday. So we're going to use this to our advantage today. Now, For both of these two, since they're actually moving in circles, we're not going to use acceleration, but we're going to use torques. So when it comes to torque, we want to write it that the angular acceleration is equal to, technically there's a negative sign here, negative the angular frequency times the angle. So remember, when you're dealing with things which are moving in circles, what happens then is your position goes to angle, your velocity goes to the angular velocity, your acceleration goes to the angular acceleration. Right? This is our replacement scheme that we had from 175. So this is replacement for angular motion. So this is what we want to do. So we want to now use these simple pendulums to then extract what is our angular frequency. So in this case, we're going to draw our mass attached to our string. Let's say our string has a length of L to it. So this thing has a length L. And we're going to displace that away from the vertical by some angle of theta. Okay. This thing keeps going back all the time, driving me nuts. So, oops. Okay, how do I move it? Okay, I can move it, guys. So, let's go over here. So basically, we're going to look at a situation like this. I'm going to put the velocity and acceleration on here. We're going to take a mass attached to a string. So this is our simple pendulum. And we're going to displace this by some sort of angle, right? So here what's happening is that we have a gravitational force downward. Oh, well, let me stop at that stage. But anyways, here I have gravitational force acting straight down. We have a tension pulling back towards the center. Those are the only two forces which are acting on it. But this thing is going to swing. As it swings, the gravitational force is pulling down, but part of that is pulling towards the center. That's going to act as our restoring force. Along the tension, there's a force. And since it's moving in a circle, there's a centripetal force. So that's why as you watch this thing going back and forth, the acceleration arrow here, the yellow one, for example, by the time it reaches the center, see if I can stop it at the center. So when it's at the center, that acceleration is pointing straight upward because that's centripetal acceleration, which wants to pull it towards the center. The velocity will always be tangential to the direction in which it's moving. Okay. So let's draw our free body diagram. Let's go back to here. Move you guys again.
I have a question.
Sure.
So we talked about how like a spring, it doesn't matter how far you pull it, the period's always the same.
Yes.
But with a pendulum, if you pull it farther, like, would it be the same or would that change things?
Well, there's a caveat here. So that's a fantastic question. So
okay, well,
the answer is, as long
if we
as
don't need to know it, then it's okay.
Oh, no, it's okay. It's a good question. So we're going to, and this is an assumption we're going to make. We're going to talk about this assumption. So as long as I pull this thing so it has an angle which is somewhat small, so here, say out to like 20 degrees as I'm pulling it here, then it turns out that in that case, it's independent of the amplitude. That will absolutely be true. So it turns out that whether I pull it so that it's only at, say, 6 degrees, then the period at which it oscillates versus if I pull it to, say, 20 degrees, in that case, it'll be completely independent of the amplitude. That's absolutely true. However, this is where our caveat comes into play. If I pull it with a much greater angle, say something like 90 degrees, and I let it go, now this is not actually simulating what would happen, but in that case, what actually happens is, so if I pull out my keys here again, so imagine if I pull it out to the side and I let it go, what you can see is that slack in the string, right? So as this thing actually starts to fall down, there's not enough tension in the string. And what actually happens in that case then is it does become dependent on the amplitude at which I pull it. What'll actually happen is if I pull it too far, my system actually becomes chaotic. So it actually goes into a chaotic system, which basically means that it won't follow simple harmonic motion anyways. Once it
Okay.
settles down, it might start following simple harmonic oscillation, but basically we go from a organized simple harmonic oscillation to a chaotic system, which is something we're not going to talk about.
Okay.
So this is a very good question. So the reason that this is going to be independent of the amplitude is because we're going to make the assumption that we're going with a small angle displacement. Okay. So basically we're going to have an angle which is much less than 90 degrees. So again, something like 15, 20 degrees. In this case, that's the regime that we're looking at. So it will be independent of the amplitude, just like the spring mass system. Now, the difference with the spring mass system is it doesn't matter how far I pull that spring, as long as I don't break the spring. Right? So something you didn't talk about in 175, but everything has a breaking point to it. So if I tried to stretch my spring too far, what will happen is I will eventually break it and it will go from being elastic to non-elastic. So imagine if you had an old slinky, right, like a metal slinky, and you pulled it. If you kept pulling it as far as you could, eventually what will happen is you're going to break the slinky by causing the coils to disappear. Now it's going to become more of like a straight line. At that case, it won't actually go under harmonic oscillation anymore because you've destroyed the elasticity of the object. Now, if you don't destroy the elasticity of our slinky, we could technically pull our slinky to the North Pole and it would still undergo harmonic oscillation. So there is no, as long as I don't break the substance, it's independent of the amplitude. For a pendulum, that's only true for, again, small angles. So as long as I keep that angle small enough, it will be completely independent of the amplitude. If I start, again, going bigger, so if I stop this thing and I start going to higher angles, something more like 45, 50 degrees, in that case, no, it would actually be dependent on the amplitude. So, but that's something we're not gonna deal with in this class. But that is a very good question. Okay. So, is that okay, Adrian?
Yes.
Good, okay. So let's now analyze our system. So here we know we have a gravitational force. So here is my mg pulling down. We also know we have a tension force. So that tension is going to be pulling along the direction of the string. So it's going to be the direction of our tension. Quick question. When you guys wrote down tension in 175, did you write it as T or F of T?
We wrote it as F of T.
F of T, okay. Sounds good. F of T, good. Okay. So, good. So again, if I look at my free body diagram, so let's write that over here. So again, I got F of T off in this direction. So here's my F of T. And again, I have mg straight downward. That's not straight down, but we'll pretend. Wow, I can't draw straight. Wow, that's even worse. These days I'll figure out how to draw. Okay. That didn't even work either. Okay, there we go. So I have mg down this way. Now again, what's going to happen is we think about the motion of this thing, right? Whoops. So if we think about the motion of our pendulum, this thing is going to be swinging like this, right? Which means it's actually not going to be the forces that we care about, but what we're going to care about is the torque about this point up here. So this is actually going to be our pivot point up here, and what we care about is the torque that this thing is going to generate. So if I think about the torque, so here, if this is my pivot point, this is my vector r, which points down to the center of this object. In this case, there is no torque from the tension, because remember that torque is equal to r cross F, which is the same thing as the magnitude of R times the magnitude of the force times sine of the angle between the two. So in this case, our R vector points from the pivot point to the center of the mass. The tension points in the opposite direction, which means in this case, the angle is 180 degrees. So this is going to be the same thing as R times the tension times sine of 180 degrees, but sine of 180 is simply equal to 0. So here, the torque due to the tension is going to be 0, but there is going to be a tension or going to be a torque from mg, because here these two are not going to be exactly in line with each other because mg points straight down. The r points in this direction, which means that the angle between the two is exactly the same as the angle which is this guy's being displaced. So here, the total torque is then going to be equal to negative, and it's negative because it's pulling in this direction, of r times mg times then sine of the angle between the two. Now here, r is the length of the distance between the pivot point and where the mass is, which in our case is simply equal to the length of the string. So it's going to be equal to minus the length of the string times the mass times g times sine of the angle between the two. Okay? Now, torque, remember, the sum of the torques is equal to the moment of inertia times the angular acceleration. So here, this is a point particle, and the moment of inertia of the point particle is simply equal to the mass times the distance r squared, which in our case is going to be simply L. So this is going to be m times L squared. So if I rewrote this, this is going to be m times L squared times the angular acceleration, then is equal to minus L times m times g times sine of the angle between the two. So this m is the same as this m, so we're going to cancel that out. This L is the same as this L, so we're going to cancel that out. So finally, you're going to write this as the angular acceleration then as minus acceleration due to gravity divided by the length times then sine of the angle between the two. Now, this is where that small angle approximation is going to come from. So here, if I displace this by only a small angle, it turns out that, mathematically speaking, sine of the angle is approximately the same thing as the angle itself. Okay? And you can check this with your calculator if you want to. Make sure it's in radian mode, but if you did, say, sine of 0.01 radians, it turns out to be about 0.01. So as long as we're dealing with small angles, so if we have small angles, meaning that our angle is much, much less than, say, 90 degrees, turns out in this case that sine of the angle then is approximately the same thing as the angle. So we're going to write this then as minus g divided by L times the angle. Okay. So what this says then is that the angular acceleration that this thing is experiencing at any point along its trajectory is then given as minus g divided by L, i.e. the length of the string, times then the angular displacement. Now, if we go back to what we wrote down here, what we said was that we're going to use the fact that the angular acceleration then is equal to minus the angular frequency squared times that angular displacement. Which means if I compare this alpha here to this alpha here, we can then read off exactly what the angular frequency is. So according to this, whatever shows up in front of that theta and after the negative is the angular frequency squared. So comparing these two says that the angular frequency squared then is equal to g divided by L, which then implies that the angular frequency for our simple pendulum is simply g divided by L with the square root. So this is our angular frequency for a simple pendulum. So this is true only for a simple pendulum. Okay. Everyone okay? Hopefully. Okay. Now, let's use this and let's do an example. So the example we want to look at is, there it is. So it says, using a small pendulum of length 0.171 meters, a geophysicist counts 72 complete swings in 60 seconds. What is the acceleration due to gravity in his lab? Okay. So what that means is he takes a simple pendulum. Here's my simple pendulum. So again, ML causes this thing to be displaced by an angle of theta. And in this case, he counts that this thing goes under 72 full oscillations in 60 seconds, where the length of this is 0.171 meters. So we then want to know, again, what is the angular frequency? So good. So first things first is if we know that this thing goes through 72 oscillations in 60 seconds, So the question is, what is the period? So if we know it does 72 oscillations in 60 seconds, how would we then determine the period?
Is it 1 over 72?
That's right. So it's just going to be 60 divided by 72. So good. So in this case, what we know is that the period of a single oscillation then is going to be 60 seconds divided by 72 oscillations. Right? This is then going to be the period. Now, but what we wrote down before, what we know is that the period is related to the angular frequency by 2 pi divided by the angular frequency. Since this is a simple pendulum, we now know that the angular frequency is going to be the same thing as the square root of g divided by L. So let's put these things together. So this says that our period then is going to be 2 pi times the square root of L divided by g. So since we know the length of the chord, we know the period now. From here, the only thing we can do is then solve for g. Right? What is the acceleration? So let's square both sides, solve for g. So this says that g then is going to be equal to 4 times pi squared divided by the period squared, all times the length of the string. So let's put all that in. So it's going to be 4 times pi squared divided by 60 divided by 72, quantity squared, times 0.71. So, look at my numbers. What I find in this case then is that the acceleration he measures in his lab is 9.73 meters per second squared. So this is g according to his lab. Everyone okay with this? Usually I look around at all your smiling faces to see how much confusion there is in class, but since nobody wants to show their face, it's hard to do. So, is everyone doing okay?
Yeah.
Yes, okay. Good. Thank you, Kate. All right, so good. So last thing we're going to talk about for today is, again, that physical pendulum. So let's look at now our physical pendulum. So let's say here's my physical pendulum. Let's say this is our pivot points. That's our pivot points. And again, we want to displace this thing by some angle. And let's say this is the location of the center of mass. So that's our center of mass. And let's define this distance here as d, which is the distance from the pivot point to the location of the center of mass, so that this thing is displaced by an angle of theta. And since this thing has a mass, we know that there is a gravitational force pulling straight down on this thing. Almost got straight, there we go. So there is my mg. So basically with this, we're gonna do exactly the same thing we just did. So again, what's gonna happen is this thing is gonna swing back and forth due to the torque, which is being generated by this gravitational force, where part of it's gonna pull it back to the center. So again, we're gonna say that the torque is equal to negative of the distance, which in this case is the distance d. That's the distance from the pivot point to the location of the center of mass. Again, this angle here is gonna be the same as this angle. So it's gonna be times the force, which is mg, times sine of the angle between the two. So here, again, this is going to be equal to the moment of inertia times the angular acceleration is equal to minus d times mg times sine of the angle, which means that the angular acceleration is going to be minus d times mg divided by the moment of inertia times sine of that angle. We're going to do the same game we did before. We're going to pretend that the angle is much, much smaller than 90 degrees. So that sine of theta is going to be approximately equal to theta. So this will again be minus d times mg divided by I times theta. So same thing as before. What we want to do is compare this to minus omega squared times the angle. So from here, comparing these two things, we can see that whatever shows up after the negative but before the theta is equal to the angular frequency squared by definition. So this is going to be equal to dmg divided by the moment of inertia, which means that for the physical pendulum, the angular frequency is going to be dmg divided by the moment of inertia about the pivot point. Okay. So this is then the angular frequency for a physical pendulum. So if I'm dealing with a physical pendulum, all this says then is that I can determine my angular frequency this way. I need to know d, where again, d is going to be this distance here from the pivot point to the location of the center of mass. M is just the mass of the object. G, of course, is just g. And then the moment of inertia here is the moment of inertia about the particular pivot point, not the pivot point about the center of mass, because if it's pivoted at the center of mass, it's not going to harmonically oscillate. So this is then the angular frequency for our physical pendulum. So now we have 3 different angular frequencies that we know of. So for our angular frequencies, we now have omega is equal to the square root of k over m. This is only true for a simple spring mass system. We have that it's equal to the square root of g over L. This is true for a simple pendulum. And then finally, we have the square root of mgd over the moment of inertia, and this is true for a physical pendulum. So again, the nice thing about all these, again, is if we go all the way back to where we started today, all of these general expressions are true for all of these different omegas. So the only thing we have to know is what type of physical situation do we have? Do we have a spring mass system? If yes, we know this is the square root of k over n. But again, that's only true for a single spring attached to a single mass. If it's something different, this doesn't work anymore. If I have a simple pendulum, it's the square root of g over L. If I have a physical pendulum, it's the square root of mgd over I. And again, if it's not one of these scenarios, we then have to go through and do exactly what we did for each one of these different individual systems, either write down the sum of the forces or the sum of the torques, and then get to the point where we isolate the acceleration. And then from there, we can read off exactly what that angular frequency is. Okay. So now that we know this, let's do an example to kind of see how this works. Okay. So let's look at, so let's say I have a disk. So here's my disk. And I want to open a bar, okay? So Keenan, let's say Keenan wants to open a bar, and he's going to write Keenan's place. Keenan, am I pronouncing your name correctly?
That is correct.
Good, okay. So this is Keenan's place, okay? So let's say that he wants to use a disk that he's going to use as the sign of his bar, where the radius of the disk he wants to use is, oh, I have the problem already brought up here. Here. So he wants to use a plywood disk, which has a radius of 20 centimeters and has a mass of 3 kilograms. Okay, so he wants the radius here to be 20 centimeters with a mass of 3 kilograms. And then he's going to drill a hole here to use as this pivot point. So this is going to be the location of the pivot point. And that pivot point then is going to be 2 centimeters from the edge. Okay. So basically, we're going to define this distance here. So here's the edge. So let's say this distance, let's call that x, is going to be 2 centimeters. Okay. So basically, this is going to be his sign outside of his bar. Now, let's say that there's a wind which comes through. That wind pushes his sign, which then causes it to harmonically oscillate. So what will eventually happen is, if he has a strong wind which comes through, this thing is going to harmonically oscillate back and forth about some sort of amplitude depending on the size of the wind. So what we want to know then is, what's the period of oscillation of Keenan's bar sign? This is what we want to know. So what is the period of oscillation? So good. So again, we know the period is equal to 2 pi divided by the angular frequency. Since this is a physical pendulum, because it's a disk, this is going to have 2 pi times the square root of the moment of inertia divided by the mass times g times d. So let's talk about all these different things. So first of all, d is the distance from the pivot point to the center of mass, which in this case is going to be this distance here. So this is going to be our d. So according to our picture, d then is going to be the same thing as the radius of the disk minus that distance of x, right? That's going to be this distance here. So if I go all the way to r and then come back x, then that's going to be d. So that's going to be what that quantity d is. The pivot point, or the moment of inertia, is the moment of inertia about the pivot point, right? So it's going to be the moment of inertia about this point up here. Now, if we looked at our textbook or online or anything like that, we can't find the moment of inertia about that point, but what we are going to find is the moment of inertia about the center of mass. So if we go back to 175, if we want to move the moment of inertia from one point to another point, we have to use what's known as the parallel axis theorem. So the parallel axis theorem says that the moment of inertia about that pivot point is the same thing as the moment of inertia about the center of mass, plus then the mass of the object times the distance we are away from the center of mass squared, which in this case is going to be that distance of d. So it's going to be the same thing then as the moment of inertia about the center of mass plus the mass times the radius minus x squared. Now, moment of inertia about the center of mass for a solid disk is simply equal to 1/2 the mass of the disk times the radius of the disk squared. So in this case, this is going to be the same thing then as 1/2 the mass times the radius squared plus the mass times the radius minus x squared. So if I put everything together, what's going to happen then is that this mass here is going to cancel this mass and this mass. So it's going to be the same thing then as what? 2 pi times the square root of 1/2 of the radius squared plus the radius minus x squared, all divided by g times the radius minus x. Okay. Plug in my numbers. What I find in this case then is that my period works out to be 1.08 seconds. So if Keenan decided to use this as the sign of his bar, again, if a stiff wind comes through, this sign is going to oscillate harmonically back and forth, again, independent of the amplitude, with a period of about 1.08 seconds. And again, as long as there's no friction up here, this will happen indefinitely until somebody actually forces it to stop. So, is everyone okay? Any questions on anything? Everybody okay? So let's do one more slide to kind of recap everything. So again, in general, what we have is that x of t is equal to the amplitude times cosine of omega t plus phi. We know the velocity now as a function of time is equal to negative a times omega sine of omega t plus phi. We know the acceleration as a function of time is negative a times omega squared times, oops, should be cosine. Okay. Times cosine of omega t plus phi. We know that the acceleration is equal to negative omega squared times x. We know that the maximum acceleration is equal to omega squared times the amplitude. We know the maximum velocity is equal to omega times the amplitude. We know the total energy is equal to the kinetic energy plus the potential energy. We know 2 pi times the frequency is equal to the angular frequency. And we know that the period is equal to 2 pi divided by the angular frequency. Again, these things are all general for any type of harmonic oscillator. Again, the only difference here is that when we're talking about pendulums, we're going to replace x with theta. That's the only difference. And then this guy would usually be omega, and then this guy would be alpha. But other than that, everything else is the same. And specifics, the only thing we need to know then is what is omega. And omega, as far as we know now, is one of three things. It's either going to be the square root of k over m, and that's if we're dealing with only a simple pendulum, or sorry, not simple pendulum, but simple spring mass system, one spring attached to one mass, or square root of g over l, and that's our simple pendulum. So a string of length m, or l attached to a mass of mass m, or now a physical pendulum of mgd divided by I. Again, the moment of inertia about that pivot point. So again, all of these scenarios here, all of these equations are satisfied in any one of these three different scenarios. If my physical situation is not one of these three scenarios, we then have to go through the sum of the forces or the sum of the torques to then determine exactly what that omega is. So for example, if I had two springs, let's call that K1, and another spring, call that K2, attached to one single mass of M, then we can't use this guy. We have to now come up with a new formula of what this thing actually looks like, because it's not the same exact scenario as that previous one. But again, the important part here is that all of these equations that we wrote down are satisfied for any one of these simple harmonic oscillators. Whether it's a spring mass system, a simple pendulum, a physical pendulum, it doesn't matter. The only thing that's going to change for each individual one is what is this angular frequency. Once I know what the physical situation is, again, whether it be a simple pendulum, a spring mass system, or a physical pendulum, I can now calculate what is that angular frequency, use it into any one of these different scenarios, depending on what it is that I want to know. So it's kind of the beautiful part of all of this. So the general part is the same regardless. The specific part just changes depending on what the object is. But each one of these only depends on the physical parameters of the problem. None of them depend on the amplitudes. They only depend on, in this case, the spring constant and the mass. In this case, just the length of the system. Doesn't even depend on the mass. And this one depends on the mass, the distance from the pivot point, and the moment of inertia. So, how's everyone doing? Everyone okay? Well, hopefully I'll take silence as reassurance. Okay, so we're basically out of time for today. So tomorrow we'll start off with our first group exercises. I was hoping to get those today, but since we didn't get to those today, we'll start with them tomorrow. So basically what we'll do is when you guys sign in, we can answer any questions, anything like that initially, and then I'll break you guys off into breakout rooms. So basically I'll have randomly assign, I'll put 3 to 4 people in these breakout rooms. The group assignments are actually already posted onto Blackboard, so you can see them then, but we'll talk about them before I put you in the breakout rooms. The point of all this is to basically discuss with each other, learn from each other, think about how to actually solve these problems, and work with each other for some peer learning. I'll be here. I'll also go into the breakout rooms and then basically check on how you guys are doing, answer any questions that you have. So we'll go over the first one. I'll give you about 15 minutes to kind of work on that. And then we'll go over the next one. I'll give you about 15 minutes to work on that. So probably at least half the time of tomorrow, we'll be working on these group assignments. And then we'll start the rest of chapter 11, which is now starting in another example of simple harmonic oscillation, which is actually waves. So we'll start our waves conversation tomorrow. So, but again, the point of the group exercises are again for class participation. And these are the things that As long as you work on them, you turn them in on the day of the exam for extra credit. So after tomorrow, you'll automatically have 2 points of extra credit going into the exam as long as you turn these things in. And again, they're also used for peer learning, so you guys can kind of work with each other, figure out how these things go, learn from each other, discuss them, kind of figure out what it is that you don't understand at an earlier stage before we get to the exam. Okay. So again, any questions on anything we talked about today? Again, I know we go kind of fast. There's a lot dumped on you every day, but so any questions, any issues anybody might have?
I do have a question, but it's
Sure.
more in reference to the lab.
Oh, okay. Yeah, that's fine. You can ask that too.
Okay, so for both part 2 and 3,
Mhm.
I got all the data
Okay.
and then I wasn't sure what to do with it. Like so for part 2, I got the periods, but then didn't know how the period related back to the spring constant.
Oh, so that goes back to actually what we talked about today. Good. Good timing. Let's see here. Where is it? Good. So that goes back to actually what we did in this problem. So here the period is related to the mass and the spring constant this way. So if we go back to from the first example we did, part A, so we have the period then is equal to 2 pi divided by the angular frequency, which is the same thing as 2 pi times the square root of the mass divided by the spring constant. So in this case, you are measuring the period, you are measuring the mass, you're just putting the mass on there, so you know what the quantity of the mass is. So from there, now you can isolate what that spring constant is. So if we write on here, so let me use a different color. So basically from here, you would then say the spring constant then is going to be equal to what? So 4 pi squared divided by the period squared times the mass. Right? So this is now going to be your spring constant. So basically from those periods, you then, and that mass, you then can determine exactly what that spring constant is.
Okay, that makes sense.
Okay. Good. And then you're going to use the same formula as well in part 3. In part 3, you're now just doing the different. Now you know K, you know the period, that's what you're measuring, so now you can determine the mass. So this would be for part 2, and then for part 3, okay, you're now just going to have that's what? So the period squared divided by 4 pi squared times the spring constant is equal to the mass. So this is what you'll be using in part 3.
Okay, that makes sense.
So yeah, so all that just comes from here. Exactly. Good.
Okay, thank you.
You're welcome, Adrian.
I have a quick question about the absolute and relative discrepancy calculation for those.
Yes.
In 175, we were given an accepted value to calculate those.
Correct.
In this lab, there is no accepted value?
Basically, that's right. So basically, you're going to assume one of them is the theoretical value and the other one is going to be the experimental value. Okay. So, so basically your relative and absolute discrepancy comes from comparing the 2 different ways of doing it. So basically in part 1, what you were doing is you were adding more and more mass on there and then plotting a best fit line to determine your spring constant. Mm-hmm. In part 2, I believe what you were doing then is you were individually measuring the spring constant for each one of the different masses based off of that displacement.
Right.
So basically, so the question becomes which one is more accurate? So which one would become your, your more accepted value? So which one would you say is more accurate? So which method to you would be more accurate of determining what the K value is?
I would think part 1 because there's human reaction time in part 2. You have to stop the stopwatch.
Right, exactly. So good. So basically, exactly. So what you'd be doing then is saying, okay, your accepted value then is going to be what you would do in part 1.
Okay.
That's your accepted value. And then experimental value is now going to be what you did in part 2. So in that case, when you're doing your relative, you're using your theoretical or your accepted value from that, what you got in part 1.
Okay, I just needed to know which one was supposed to be the theoretical value.
Right. Yeah, in a situation like this, as you said, we're not just giving you the number, so it's a little bit more difficult to say, but
Right.
But exactly. That's right, Katie. Good.
All right, thank you.
You're welcome. Any other questions on the lab or on what we talked about in class, or? It's doing okay? All right, last thing I'll leave on is don't forget that those conceptual questions are due by 5 o'clock today. I won't post any more until tomorrow. Those will be due on Thursday. And obviously I won't post any on Friday because we don't have class on Friday, so we're only going to have the 2 conceptual questions this week. Don't forget we don't have class on Friday this week. That'll be part of our 4th of July celebrations. And other than that, I'll see everybody tomorrow. Like I said, we're going to start off with the group assignments tomorrow. They are on Blackboard, so we will talk about them before we go through them. But again, if you can't see them, at least they're already on Blackboard, so you can look at them that way. And we'll just randomly assign different people to work in the different breakout rooms. So be ready to talk to each other tomorrow. So don't be as silent as you are when you're usually talking to me. So it'll be great. All right. So having said that, I'll see everybody tomorrow.